All right, cool. Hi, everybody. This is Taking Event Correlation with you, and my name is Rob King. And that is the last time I'm going to just read a slide to you. So, I am required by Nevada law to tell you who I am, so I'm Rob King. There's my email address. And yes, it is actually J, not R. It's a middle name thing. I actually grew up in small town Texas, and I was like 27 before I realized that my nickname could have been Jim Bob, so yay. Anyway, but that's my email address. I'm going to repeat it at the end of the talk so that if you decide it's actually interesting and you want to email me, you can do so. The rest of the stuff is not particularly interesting, except that I kind of have done this sort of stuff before, so, you know, yay. The talk's the interesting part. So, I always wanted to do a professional presentation that started with Webster's Dictionary defines, but there's no actual definition of event correlation in Webster's Dictionary. So what do I mean when I talk about event correlation, right? Well, what are events? Events are all the little things that you might care about, right, going on in your network. A web request, a login, anything like that. Anything can be modeled as an event, right? And event correlation is extracting information from that aggregate set of events, from that stream of events, right? And that's what we're going to be talking about during this talk. And the goal of this presentation specifically is to introduce a new open source tool called Giles, right? And Giles is a compiler that makes it easy to build event correlation engines. Giles itself is not an event correlation engine. It helps you build event correlation engines. It's a teach someone to fish versus giving them a fish kind of metaphor. I don't know. So it makes it easy to build the kind of event correlations that engines that we're talking about. And it makes it easy to find patterns defined by complex predicates. And what do I mean when I say complex? I don't mean difficult. I mean multiple relationships, right? Not simple, not just A equals B, right? Complex predicates in large, constantly changing data sets. And that's also something that is maybe important to note. Constantly changing data sets, you know, you often have in this sort of in these sorts of systems, you might be able to deal with large data sets, but only through a very narrow window, right? So the last 5 logins, the last 10 minutes, something like that, right? And I want to talk about engines that are holistic. They deal with your entire data set, even as changes trickle in or trickle out, or, you know, however they come in and out. And this is the gimmick of Giles. It makes it very easy to integrate this sort of stuff into your existing environment, right? And I don't just mean your existing software. I mean your programmers already know how to use Giles engines, right? And it's a little gimmicky. It's not that gimmicky if you actually read the blurb for the talk, but it's pretty cool. So, before I talk, though, about how Giles actually works, I want to talk a little bit about how it came to be, because that informs the design decisions, why we designed it the way we did, right? So back in 2010, might have been 2011, I don't know, it's a long time ago, CoreLogic was contracted by DARPA, the Defense Advanced Research Projects Agency. They invented the internet along with Al Gore. That joke never gets old. Timely joke. Was contracted by DARPA as part of a multi-year contract as part of the Cyber Insider program, CINDR, to develop a product that protected the software development lifecycle, right? Specifically, it was monitoring for malicious insiders in your source code management system. So not looking for like shell code in your source code or anything like that, but looking instead for nefarious behaviors in your source code management system, right? And that product was called DIRT, which stands for Detecting Insider Repository Tampering. And it's a fascinating product. It's completely awesome, but it's not the subject of this talk yet, sort of. But DIRT, you know, so DIRT was delivered as an appliance. It was an actual physical thing that went there because people didn't want their source code, you know, leaving their network, which makes sense. And DIRT modeled the source code repositories as sequences of change events, right? So it wasn't just looking at the source code repository, it was actually saying, oh, okay, now this changed, change, right? So we needed an event correlation engine, right? But because it was an appliance and because it was not going to be under our direct control, you know, it had some pretty strict requirements from the engineering standpoint. It needed to be able to run unattended. It needed to be able to handle large amounts of data, right, reliably. and it needed to integrate well. It needed to impose very few additional requirements because it was just one piece of a bigger puzzle, right? And so that ended up being a tool called Giles. And Giles is now open source. And, you can download it and it's awesome. So that's what we're going to talk about is Giles. So how does Giles see the world, right? Giles sees the world as a collection of facts, right? And I realize that we're talking about events and facts are interchangeable. You can use the terms interchangeably. We call them facts because Giles can be used to build things that aren't event correlation engines, right? And can also describe things that aren't events, But a fact is just a statement that's true in our problem domain, whatever our problem domain is, right? So it could be a statement about a person or an object. Suzanne is an astronaut. Could be an event, something that happened, like train I arrived at platform 9 3/4, which, I'm that big of a dork. Come on, that's awesome. Train I, because it's, okay, whatever. It can also state just things about notions, like the user's preferred language is, Canadian French, which, isn't everybody's. Or, more salient to the kind of thing that we deal with, events on your network, right? User John Doe logged into terminal 33 at 5:10, right? That's a fact. That's something that we assert to be true. And then just repeating myself, we call them facts instead of events. So, all of the facts that we're dealing with, right, at one time is called our working memory, right? And so here's a collection of facts that we got from a file called var log logins, which probably doesn't really exist, but whatever. And that's important to know. Facts can come from anywhere. We don't care where they come from. We just care that they are what they are. So here's this collection of facts. It's just kind of a bag. We can extract some information out of it. We can see that there's a failed login. We can see that there's usernames, that sort of thing. But what we really want to do is get as much information as possible out of these facts, right? That's the point of event correlation. So what we can do is we impose structure on facts, right? So we immediately, this immediately becomes much more clear what we're talking about, right? And the preferred nomenclature dude for that is fields. Those are the fields of facts, right? And so you can immediately see that this is much more clear. You have the status, you have the username, login time, terminal, all that good stuff, right? And then Giles even goes one step further and actually imposes type information on those fields, right? So you're not just dealing with login successful and it could be whatever. You know that it's going to be a Boolean, right? And the type system it's very simple. It's Boolean, string, integer, real. Nothing crazy, nothing complex. And we'll get into actual practical Giles here in a second. I just want to make sure we're all on the same page about the problem we're trying to solve. But facts are just data. They're just information, right? The whole point of it is that we want to get knowledge. We want to extract knowledge out of those facts, And how can we do that? Well, we do that by looking at patterns of facts, by asking questions, by seeing what sets of facts match a given pattern, right? And sometimes all you got to do is do grep, right? I mean, you could just grep for failed logins, and you immediately get all your failed logins, right? It's very simple. You're correlating events there, but it's just one event at a time, which is fine. And I'm a big fan of doing the least amount necessary. I'm very lazy, so if grep works, more power to you. Please use grep. But that's not what I'm talking about when I say complex event correlation, right? So let's make it a little bit more complex, right? Now we're going to say we don't just want to see one failed login or all the failed logins. We only want to see things where you have some number of failed logins in a given time frame, right? And suddenly that makes things much more complex, right? And this isn't the end. It gets more complex than this. But immediately we have to deal with, we're storing state, right? We have to store the username. We have to store the start time. We have to store our current count, right? So we're suddenly it's a little bit more than just watching a stream of events go by. We have to maintain some state on the back end. And it also starts raising some questions, like whose clock do we use? Let's say, for example, do we use the wall clock? We can say, oh, this happens in 5 minutes, 3 failed logins in 5 minutes. But what if one of those was delayed, right? What if there was a network outage and that event never made it to our sensor, or made it 10 minutes later? We don't want to miss it, right? So we need to use the time field in the records themselves. I mean, we do have to trust that our sensors populate their times correctly, but If you can't trust them to do that, you can't trust them to tell you anything anyway. And then when do we reset the timer, right? Looking at this example here, let's say that we wanted to see 2 failed logins in 5 minutes, right? There are 3 ways that you could calculate 2 failed logins in 5 minutes. You could have the first 2, you could have the second 2, or you could have the first and the last, right? So do we want all those? Do we want just one? Do we, and there's no right or wrong answer there, but if you're like me, and I know I am, I want to see it all, right? So there's no right or wrong answer, but that's the right answer. You want to see everything. But now let's do something really complex. Let's ask a very complex question about a set of facts, right? We want to see, and this is going to be a word problem because I can't draw. We want to see if somebody maybe is sharing their password, right? Or somebody's password has been compromised. So let's look at Bob, okay? Bob works somewhere where there are physical terminals that you can't log into simultaneously. You can't remote into them, right? And I worked for Whole Foods for a long time in their corporate headquarters doing networking stuff. And so when I was thinking of this, I was thinking cash registers, right? Like you don't want people logging into 2 different cash registers at once because the world might end. But it could be anything else, it doesn't matter. So if Bob logs in to terminal 1 at 147 and then terminal 2 at 149, and we know that terminals 1 and 2 are geographically separated, right, in space, and he did it, in such a short span of time, then we can conclude that at least one of those logins was impersonated, right? At least one of those logins was not Bob, okay? And so this is getting a little more complex. This isn't just looking at, one event at a time or anything like that. It's actually looking at more complex things. So let's see how we would actually ask that question, right? What would we say? So we would say, well, there's login fact 1, right? Bob logged in. There he is at terminal 1 at 147, okay? Then he logged in again at terminal 2, right, at 149. And then we can ask ourselves, okay, and by the way, when I was making these slides, my 4-year-old pointed out that this slide does look like a butt. I know it looks like a butt. You don't need to tell me. So thank you, James, for saying that. But it does. Anyway, but it's a comparison, right? We're looking at the comparison. So we're asking a complex question. The question is these collections, this conjunction of predicates down here at the bottom. We want to see user 1 equals user 2. We don't care if it's success or fail. We might, but in this case we don't. Terminal 1 can't equal terminal 2. And time 1 is less than or equal to time 2. And time 2 minus time 1 is less than or equal to minimum time, which, whatever that is. We could calculate that dynamically. We could set it. It doesn't matter. Point is, that's how we ask that question, right? So we've asked the question, but now how do we get the answer out? How do we get our answer back from whatever our system is, in this case, Giles? And there's, different systems do it in different ways, but the way Giles does it is very simple. It just asserts a new fact, right? So your working memory, after it sees these 2 facts with that comparison down there, you'll suddenly get a new fact in your working memory that's an alert. And there's nothing magical. Alert's just a name. There's no predefined alert or anything like that. And so that right there opens up sort of the general working mechanism of how you work with these sorts of engines. You feed in facts, and then you occasionally ask, hey, is there anything interesting that happened, any new facts that I care about, right? Like any new alerts, And so this thing at the bottom here, and I really wish that I had put like a circle around it or something, but I didn't. This thing at the bottom is called a rule, right? R-U-L-E, because it felt like I said that funny. Rule. The comparison is called the predicate, and the assertion of that new fact is called the action, right? So when your predicate matches, your action fires, and you get a new event or whatever. You could also suppress events, you can do other things, but whatever. So rules are predicates plus actions. They're also called productions, which is why it's called the production rule system, it blah, blah, blah. So, doesn't matter. Lots of nomenclature, there's so many to choose from. So now that we've got this idea of how we're doing it, we have more questions though, right? Like now that things have gotten a little more complex, we have to ask, okay, do we want to detect everything? Like I said, I do want to detect everything. So how do we detect all of those impersonating logins, right? So, let's look at Bob. He logs in at terminal 1. This guy logs in a lot. He does a lot of logging in. Then he logs in again at terminal 2. Then he logs in again at terminal 2, right? And you'll notice there's only 1 minute difference between each, right? Well, if we only kept track of, say, the last event or we just watched it as a sequence or something, the most we would get is one alert out of this, right? We would just get an alert for the first login to terminal 2. Because the second login to terminal 2 isn't bad if we only have a little bit of state. Because remember, our rule says that the two terminal names can't be equal, right? So this is not what we want. What we want is something more like that, right? Where we detect both of those malicious logins. And logins is just an example. It's I also did, I was playing around with this, credit card swipes. Like if I swipe my credit card in Austin, Texas, and then I swipe it again in Las Vegas, and then I swipe it again in Las Vegas, maybe something's up. Just because I did it twice in Las Vegas doesn't mean Las Vegas should win. Although Vegas always wins. So we want to detect that, right? So this is a question that we need to ask. How do we detect both of those malicious logins? Or suspicious. We don't want to cast aspersions. And then how do we handle out of order reporting, right? So let's say that the building that has terminal 1 in it, right? We'll call that building 1, has a network outage. Okay, so it's not sending login events to our central collector, right? But the building that has terminal 2, which we'll call building A, is sending events, right? It still has network connectivity. So what happens is it comes in order, okay, or it comes out of order rather. So you see the 2 logins from terminal 2 before you see the login from terminal 1, right? And that's obviously, do we want to miss that? I mean, in some situations that might be fine. But not on my watch. I want to see that. When building 1's network connectivity comes back up, I want those events to come in, those facts to come in, and I want to correlate everything, and I want to say, hey, I saw 2 suspicious logins, right? We still want to see that. But then there's still even more. How do you handle retraction of facts, right? Do you handle it at all? Maybe you don't. Although actually there's if you don't handle retraction of facts, doing out of order stuff gets difficult. But anyway. Say, for example, the manager in building 1 says, oh, yeah, I was testing something. I used Bob's login. That wasn't malicious, right? That wasn't suspicious. And so you want to retract that login event from building 1, right? But when you do that, you want that alert to go away, or both of those alerts, right? You don't want to leave, spurious alerts around. So how do you handle that? How do you handle that particular thing? And then how do you scale that? How do you scale that to thousands or millions of these facts floating around, right? And the answer, at least for the purposes of this talk, is Giles, right? Now that we know about event correlation, we've come such a long way, you and I. So Giles, this is the cool thing about Giles, right? Remember all of the engineering decisions we had to make, where it had to run unattended, it had to be data safe, it had to do all this cool stuff, right? So that sounds a lot like a database, right? And so that's what Giles does. Giles takes a description of an event correlation engine and spits out a schema for a SQL database, right? You can use any SQL database you want as long as it's SQLite. And you take that database, and when you create a database from that schema, that database is a complete, standalone, no external dependencies, no runtime dependencies, no extra libraries, nothing, event correlation engine that you interact with just by inserting and deleting and selecting. You don't even have to do complex stuff. It's great. And that immediately lends some engineering wins to this, right? This approach immediately has some wins, right? Because your programming team already knows how to interact with a database. If they don't, then they should probably learn, because we use databases a lot. You can use pretty much whatever language you want, right? Pretty much every programming language has bindings for databases, right? You might not have bindings for Drools or something like that, some other big rule engine in your language, because you're awesome and you're writing in Haskell. That's great, but yeah. Or my poor colleague who had to do everything in Visual Fox Pro. That was painful. And actually, speaking of cool languages that nobody uses, anybody use Rebel? Anybody raise your hand? Rebel? No. Old Amiga? No. Okay, fine, whatever. Giles was almost written in Rebel, but it's not. It's written in a beautiful dialect of Ruby that's so much better than regular Ruby called Python. And so those engines that Giles creates, they handle out-of-order assertions of facts. So you get all those benefits of just using a regular database, right? And immediately you get all those great benefits just for free. You also get, it crafts the schema in such a way that you get out-of-order assertions are handled cleanly. You scale to millions of these facts because databases, there are a lot of work's gone into making them scalable, right? So you pick up on all that scalability just for free. You handle fact retraction consistently, very important. And this is really neat. Like this is one of my favorite little gimmies. The engines can reveal their reasoning process to you, right? Which means that, not only will they give you an answer, but they'll tell you how they got it, right? So in your face Prolog. So any Prolog programmers out? You know what I'm talking about. Yeah, okay. So, and then run efficiently in time, right? And this is important. Like a lot of people seem to think that, oh, this is just doing some sort of complex, queries. It's doing a join or something, blah, blah, blah. No, it does more than that. It's much faster as a result. And I'll talk about that in a minute. And then I'm going to do a live demo. But before I do a live demo, demo gods help me. Before I do a live demo, I want to talk real quick about, I want to be very clear about this whole retraction reassertion thing, right? So Giles engines have what's called the Giles guarantee, right? It's a fundamental guarantee of how the engines work. For the default engine type, there's the development version of Giles has like statistical engines and stuff. This doesn't apply there. But for the default engine type, this always works. So when you give it a fact from outside the engine, right, from a sensor, from a person, whatever, we call that an axiom, okay? And that's basically just saying that it isn't a fact that the engine produced as the result of some sort of rule, right? Like it came from outside the engine. And the guarantee is twofold. All facts that can be derived from the current set of axioms, given the current rule set, will be derived. And no facts that cannot be derived from the current rule set, given the current axioms, will not be derived, right? So you're never going to get something that's unprovable, right? Everything in a Giles engine can be proved, okay? So in your face, Bertrand Russell. Woo! This should have been a delay here. Okay, so and just to give an example of how consistently this is applied, let's say fact A comes in, right? And you get rule 1. Rule 1 sees fact A, and as its action, it creates a new fact B, okay? That's pretty standard. And then later on down the line, fact C comes along. And rule 2 sees fact C, and rule 2's action is to retract fact A, right? Pew! Little laser sort of thing. Retracts fact A. What happens? Fact B is gone. Because fact B is no longer supportable because something else destroyed fact A, right? Now, here's the kicker. This is what's really fun, and I wish I'd illustrated this. Anybody want to guess what would happen if fact C got retracted? B comes back, A comes back, and then B comes back. Everything is consistent. Boom. It's really neat. It also, I pulled my hair out. My glorious, luxurious hair got pulled out over getting that to work right. So, okay. Now, who wants to see a real live demo? Everybody but me, right? Because, it's very nervous, very nerve-wracking. Okay, so let's see here. I've got 2 windows open. See, look at me. All right. So let's look at a Giles engine. And I'm going to open up the Giles engine here. Engines can be written in a variety of formats, but the YAML front end is the best supported. And that was an executive decision because we wanted to have engines be manipulatable with external tools, right? So you can write you can use your YAML parser to write Giles engines. It's useful. So can everybody see this? My vision is terrible, so tell me if this is too small. Is it good? Everybody good? If you can't see in the back, tell me. I'm serious. Okay. All right. So engines, they can have an optional description, right? And not to hold you in suspense, but we're going to write the engine that we use for the examples, right? We're going to detect logins to 2 different terminals. Okay. And there are better ways to do this. Like, I'm sure some of you out there are already thinking, oh, I could do this better. Yes, you most certainly could. This is not the best way to do it, but it's the easiest to illustrate. Okay. So there's our description. It's pretty simple. It just says, this engine detects blah, 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 blah. And that's for your benefit. It doesn't get compiled anywhere. Then we define the kinds of facts that we care about. Okay? So we're going to define 3 kinds of facts and call these fact classes. First one, we're just going to define preferences. And all that is we're going to be able to set our minimum time. That way we don't hard code it at 30 seconds or whatever, right? We can change it around. And then we're going to define login record, right? And that's the login record that we've been dealing with, right? So username, successful login, terminal login time, right? And then finally, we're going to define the alert class, which is just going to be what we spit out when we actually detect a suspicious login. And then you have some set of rules, okay? The only rule that we have is logged in 2 different places, right? The rule itself also has a description, and you can see that there's some magic going on there with this, this little bang expr here. So all that is, if you haven't used YAML, YAML has what's called tags, which are not anything like HTML tags or XML tags. But that bang expr just says, okay, you know, process this differently. And the Giles engine, the Giles compiler, when it sees that, it passes the string. Like this would normally just be parsed as a string by YAML, but when Giles sees it, it passes it to a little shunting yard parser, operator precedence parser to do math, you know, math. So, or in this case, string concatenation, which is like math but with strings. So you can see there, you've got this little Perl-esque dollar username going on, right? So that's a local variable that we're going to end up assigning somewhere. Local variables are how we do correlation between events, right? Between facts, okay? Every set of facts, every set of facts that matches a given signature gets its own instance of local variables, right? Excluding the empty set, and I already made my in-your-face Bertrand Russell joke, but in-your-face again Bertrand Russell, the empty set doesn't count here. So, and then you have every engine has a match all, right? And all this is and you have match all and match none. And then the development version, you also have some other crazy stuff like repeat and match sum and blah, blah, blah. But once again, I don't want to sell anything that doesn't exist yet. So right now, you just get match all and match none, which, as the name implies, is everything for that one. And then if any of those match, it's none. You know, you don't match. And then you get this little dash here is just a YAMLism saying that we're talking about a list. So we've got a list of facts to match. So first we're going to match our preferences, right? We give it a meaning, which is just a little human-readable string that we can spit out later that says this is what we mean when we see this fact, right? This is what this fact means to us. And then we assign something, a local variable called time interval, using the fields of that event, right, of that fact. And so that's what this little caret over here means. The caret means extract the field from this event. So we're saying here min time, you know, when you see a preferences fact, grab the min time out of it, stuff it in time interval. And this can be more complex. Like it doesn't have to be, you know, you could do this, you can, you know, do that, it doesn't matter, you know, blah, blah, blah. You can do crazy stuff, doesn't matter. It's an expression, but in this case the expression is just min time. And then we look for our first login record, right? And remember, there's no checking on it here. We just grab a login record, we extract the username, the terminal, and the login time, right? And we stuff them in local variables again. And then the magic happens. Look at the magic. This is the magic part. It says, now we look for another login record. This would be login fact 2, right? And we attach a predicate to this one, right? And it says, and the default predicate is just everything. So, but in this case, this is not a default predicate. This matches only certain things. And this is an encoding of that comparison table that I showed you earlier, right? Username equals username. And you see how we're comparing the field to the local variable, right? So the field username of our second login record is equal to the local variable username that we extracted from our first login record. Terminal does not equal terminal 1. Login time is greater than or equal to time 1, and then login time is less than or equal to time 1 plus time interval, right? And then we have our action, which is just assert a new alert, right? And there's, you know, we assert the message, blah, blah, blah. So that, you know, hopefully that doesn't look like super duper scary. The syntax is not exceptionally beautiful. The original version had I don't know if you can tell I like writing compilers. The original version had a Oberon syntax. And everybody was like, oh, Oberon, that's a language I've never heard of and hate the syntax of. So no, so we don't get to do that anymore. But one day, there's going to be an Oberon syntax for it. Oberon-like syntax for it. So anybody use Oberon? No? No? Okay. Nick Lauswirth invented Pascal, one of them, it doesn't matter. Okay, so I like programming languages. All right, so let's compile that engine. So we're going to compile it, example SQL, that's, you know, -o, just like GCC. And pull an example YAML, and let's watch it not work because it's a live demo. Oh, nope, look at that, worked, okay. So now, and just to give you an idea, let's look at example SQL. And when I say look at, I just mean count the lines of. It is, in fact, quite large. You just got 1,600 lines of SQL that you are glad you didn't have to write yourself. So let's actually now create. We're gonna create our own little knock here, right? So I created a script, and it's very, very simple. All it does is sit there and selects out alerts. Can everybody see that? I realize that this is not zoomed in. Sorry. Is that better? Maybe? Okay. It selects out alerts from the database and just sits in a loop and just keeps selecting, right? So let's look at our, do we have, does alertsDB actually exist yet? No. Okay, so let's actually create alertsDB real quick. You'll notice that that is just a regular old SQLite instantiation. I'm not doing anything special, nothing up my sleeve. And then I'm going to read in our example SQL. This is my burner laptop, and it's got like the world's slowest hard drive, so just forgive me. Come on, you can do it. There we go. Okay, and now let's start watching for alerts. Which thankfully there aren't any right now. That would be really confusing if there were. Okay, so now look at me. I'm going to start interacting with this completely normal database as if it were just in fact a database. So let's insert our preferences first, right? So let's do Giles preferences facts. If I misspell something, yell out because I don't have to go back and type it up. Giles preferences facts, was it min time, values? What do we pick? Let's pick 30 seconds. Okay, great. No alerts, which is once again good because there shouldn't be. And then now let's have Bob log in here. And you'll notice I'm not doing anything magic, I'm not doing anything complex, I'm just doing an insert, right? And I don't have to do any crazy selection or anything like that. So is it username, login time, success, and terminal. And what was his name, Bob? Are we picking on Bob? Let's pick on Bob. He logged in at, what would that be? That would be what, like early in the morning on January 1st, 1970, if we're doing Unix epoch. So yeah, so that's when he logged in. It was a successful login, and he logged into terminal 1. All right. Notice no alerts. Wait, I'm pointing at my own screen. Notice no alerts. Okay. So now let's have him log in again at, say, 1029 to terminal 2. Dun, dun, dun. Oh, no. Bob's password may be compromised, right? And there you go. That's the magic of Giles right there, which, okay. Remember in the iPad demo, the original iPad demo, when they made working with spreadsheets with your fingers look awesome? I just did that with SQLite, so everybody be awed. So this is basically how it works, So think about it for a second. Can your programmers instantly pick this up? Yes, they can. You can instantly integrate this anywhere you want. So now let's say, okay, I'm getting a lot of false positives with that 30-second window. It's not working for me. I don't like that 30-second window, so let's increase it. So preferences go away, alert goes away. Here, I can just, yay, command history. Let's call it 60 seconds, right? Uh-oh, that did not work. 1029, 2060. See, the live demo is going to kill me. Why did that work? Let's try 30. Oh, 60, because 60 is greater than, I'm an idiot, sorry. 20 seconds, there we go. Let's try 20 seconds getting false positive. Sorry, basic arithmetic. There we go. Alert did not come back. Okay, God, I thought algebra was broken for a minute. Okay, so, all right, so see, the alert did not come back, right? We say, no, I am in fact, I do want that 60-second window. So let's get the alert to come back. Boom. Okay. So now let's look at what those actually look like. And let me show off something else just real quick, and then we can go back to playing with this for a second. So let's look at it. It's more than just let's look at what they look like in the database themselves. So let's look at the alerts that came out. All right. There's the alert that we just saw over in the other window. So something that Giles can do, or Giles engines can do, is we can ask it to justify its reasoning, right? It's not enough to say that Bob's password may be compromised. We're a forensic-minded crowd. We want to know why Bob's password, why we think Bob's password has been compromised, right? So what we can do is we can justify it. We can ask the database to justify the fact. So justification, I cannot type. All right. So there's your justification. The engine spits out, fact alert number 3 was produced by rule logged in 2 different places, Bob's password may be compromised, blah, 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 justification. There was a minimum time period as specified by preferences number 4. So we can recursively go back and look at preferences number 4, which was the one that we had. Bob logged in terminal 1 at time 1000, whatever. So the point is you can do this for any fact. You can say, I want to know why you believe this to in fact be true. And then you can recursively justify stuff. Now the justification for the other things isn't particularly interesting because they're all axiomatic, but just to show it. So justification from Giles, what do we call them? Login record? Login record, yeah, login record facts. Where ID equals 1. No, so, not facts, justification, sorry. Yay! It just says it was injected from an external source, right? Because that's where it came from. It came from me. I'm the external source. So that's pretty much, how am I doing on time? I've got a little bit more I want to talk about, and then let me show you just one thing real quick. If I want to, does anybody want to see any more live stuff? Let's just while I have it up, let's break for about a minute. Is there any questions about the live demo that would be best answered right this second? Don't be shy. Don't be shy. You can also ask at the end of the talk, but then I won't have it up on the screen. So, no?
Where are you actually running your engine? I missed it.
The engine is entirely inside SQLite. It converted. It is running in. I'll get to that in a second. I'll explain exactly how in a second. But basically, it turns SQLite into an event correlation engine. I'm sorry? Yeah, it uses triggers, exactly. It uses a lot of triggers. And that's actually a great segue, which is, if you've ever actually read the word segue, it is not pronounced like it is spelled. Let's talk about how we actually, real quick. Advantages of Giles. We already talked about this, so I don't want to keep going, but you could run your event correlation engine anywhere you can run SQLite, which is everywhere, pretty much, including my phone, which is why the talk is called Taking Event Correlation With You, because people like running things on their phones. At least a lot of people do. My wife doesn't. She actually just got her first smartphone. They just call them phones now. She keeps saying it's a smartphone. No, it's just a phone now. We don't call it, anyway. She just got her first smartphone 2 months ago. You can use your existing database APIs, right? Your existing expertise. You already know how to access databases. You already know how to use Giles. You can have transactional semantics. This is actually really cool. So remember that Giles guarantee I was telling you about? Every time you insert a new fact, you can do that inside a transaction. So it's guaranteed that when that statement finishes, all possible consequences of that fact have been accounted for, right? It's atomic transactional semantics, atomic insert. And then the tool itself is open source and commercially use friendly, so please go do whatever you want to do with it. It's completely awesome.
Something that's not clear, you say anywhere you can run SQLite, but you're also talking about other databases. Is SQLite it?
Right now, SQLite is the only database that's supported. There's a certain minimum set of features that the database has to support for this to work. And Postgres, I'm currently researching Postgres. Postgres should be able to handle it just fine. MariaDB and MySQL cannot handle it. Their trigger handling just doesn't work right for this sort of thing. And Microsoft SQL might work. I don't know. I've never used it. Probably, maybe. People seem to like it. If anybody wants to give me $10,000, I'll port it to Oracle. So it'll be great. No, I like Oracle. I'm not trying to be, I'm sure they're worth the money. I don't have $10,000. Okay, I got 5 minutes. All right, I got to work. So uses for Giles engines. So let me just plow through this real quick. Obviously forensics. You don't have to do event correlation engines, right? Giles engines are actually instances of what are called production rule systems, which are the basis for a lot of expert systems, artificial intelligence stuff, action selection mechanisms, blah, 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 blah. And so one of the cool ones is record linkage, right? So remember that you have this automatic guarantee of everything sort of coming out in the wash, right? So what happens if you have a big collection of documents and you're trying to associate documents with people? And you put in a rule that says, oh, by the way, today I learned that a common nickname for Robert is Bob. Well, immediately, not just for any documents that are added later, but now documents that have ever been added will say, oh, Bob, oh, that's also Robert. We can link those two records together, right? And it happens, more or less instantaneously. Log analysis, event correlation, decision systems, diagnostic systems. There's one of the examples in the Giles source directory is an expert system that detects reverse traffic flows in networks. So if you say, this network has a security clearance of 50, and this one has a security clearance of 30, and then there's a bidirectional connection between these 3 networks, and blah, 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 you'll get alerts saying, oh, you can get traffic to this network by this route that you didn't know about, maybe. So it's cool. You can build lots of cool stuff with it. And if I had more time, I would have shown you that. That's called TARNIS. Not TARDIS. Everybody thinks it's a Doctor Who thing. It's not. It's TARNIS. It's an obscure Buffy the Vampire Slayer joke, as is the name Giles. So, although TARDIS is also fine. I love Doctor Who. It doesn't matter. All right. So performance. So everybody asks, how is this different from just running a SQL query, right? Is this any faster than running a SQL query? And I'm going to tell you the same thing I told them, which is smoke bomb and run away. No. So a regular database, if you run a query and you already have T facts, right, in that database, and you add N more, then it's going to be on the order of T plus N to check for new matches, right, every time. Whereas with Giles, and this isn't the best case and the common case. Worst case, it's just as bad as the other thing. You can write slow code in any language, so don't yell at me if this, if your engine does not perform at peak efficiency. But Giles amortizes the cost of pattern matching over the cost of insertion. So adding N facts to a database, to a Giles engine that already has T facts, only takes N time. So if you have 1,000,000 facts and you insert 1, it still takes the same amount of time as if you'd inserted 1 fact in a database with 0 facts, right? On average, best case, general case. And it does that via a magical algorithm called READY. And before somebody yells at me on this one too, I have heard this pronounced ready, reet, ret, and ready. And it is, I say reet, it's a Latin word. If anybody out there speaks Latin, tell me how it's supposed to be pronounced, because I just picked ready. But it's probably ready, but it doesn't matter. So this graph here, I'm not going to go into details. This graph is not meant to be illustrative of what's actually happening. It is illustrative of what's actually happening. We're not going to go over it. It's just to let you know that there's something a little more magical happening under the hood. This was developed as part of the OPS5 expert system shell back in the 70s, I think. No, it was later than that. Anyway, it doesn't matter. And what happens is it basically builds a discrimination network where you feed facts in, they trickle down through this discrimination network, and then eventually out pops your new facts, right? And that's what Giles does. Giles, in a very real sense, Giles could be called an implementation of the READY algorithm in SQLite's trigger language, right? And when I say in a very real sense, I mean literally, like that's what it is. It's an implementation of the READY algorithm in SQLite's trigger language. And so just, it's each one of these little circles here is called a memory. The memories just become tables. Each edge between those nodes becomes a trigger. The alpha predicates, which we can use to cheaply prove that a fact will never match anything, we just use those. We create triggers that suppress their insertion. So we don't waste time correlating facts that could never possibly match, right? The compiler rewrites the expressions to be more amenable to query optimization. So it looks at modern query optimizers and figures out the best way to rewrite the expression. And then it also computes a minimal covering index, set of covering indexes, right? So every expression is covered to the greatest extent possible by an index, so that you're never doing full table scan. You can do full table scans if you write your engine wrong, but we try really hard to not make that happen. And so that's it. So, just to reiterate, complex event correlation engines have great applications in I said I wasn't going to read any more slides, so I won't read it. I'll just paraphrase. They don't have to be complex. You can write engines that aren't that hard to use, right? And they're just normal databases. So you immediately get all the benefits of normal databases. Ease of use, ease of access, data safety, transactional semantics. It's all awesome. And then you can reach me. Here's my email address again. Remember, it's J, not R. And yes, I could set up an alias, but I'm not going to. It's the principle of the thing. jking@deadpixie.com. And the Giles source code itself is available at CoreLogic's Git repo at that URL right there. So, thank you. Does anybody have any questions? I specifically stopped early for... Hi, yes?
If you have rule
changes? If you have rule changes, do you have to, what do you,
Oh, I'm sorry. Sorry, can you go first and then you?
oh, sorry.
Oh, sorry. Yeah, I'm sorry. Say that again.
Did you rule out some of the existing CDP systems for reasons like Esper?
Yeah, so we looked at, he asked if we had ruled out some of the existing complex event processing systems like Esper and others. We did for a variety of reasons. There were often, they had to be zero cost, they had to be low maintenance, they had to be accessible from both Perl and Python, they had to be permissive licensing that allowed commercial use, blah, 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 blah. So at the end of the day, we ended up writing our own. So, thank you. And I'm sorry, what was your question?
When you have rule changes, you have to reload the data.
Yes, so the rule changes are, that is something that is a little hackish right now. So the way it works is when you want to do a rule change, you recompile the schema, and then there's a trigger program in each database that serializes out all the facts as triples, all of the axiomatic facts as triples, and then you attach the other database, load the triples back in, and Bob's your uncle. It's not great, but it works pretty well. So, thank you. Any other questions? Yes, sir.
What happens when you have contradictory rules or circular events?
So Giles supports, I'm sorry, the question was what happens when there's contradictory rules or cycles in events. So Giles, first off, if you try to compile an engine that has blatantly contradictory rules, the compiler will error out. If you compile an engine that has cycles in it, the engine will complain unless you pass the -C flag saying you acknowledge that there are cycles. And there is one of the actions, in addition to assert, there's also assert distinct, which means assert a fact if and only if it doesn't already exist. And that also participates in the Giles guarantee. So if that fact gets banned, gets retracted somehow, another rule that would have produced it won't produce it. So. Any other questions? Anybody? Anybody?
Your login didn't include a logout. Your login check.
You're right. It didn't. You're right. So that's left as an exercise to the reader. So. Any other questions?
Yeah.
Oh, yep. Sorry.
Biggest implementation?
I'm sorry?
What's the biggest implementation you've got?
The biggest implementation we've got was Dirt, which analyzed very large source code repositories, including the Git repo for the Linux kernel, which, using Dirt semantics, came out to be 33 million events on the first import, and it processed that in about 2 hours. So, yeah, it's not the fastest engine, but it's it's pretty good. So, anybody else? Oh, I'm sorry. Yes.
Any plans for MySQL support in the very near future?
Not in the MySQL right now does not have the trigger support that we need. The semantics. Postgres I think does. MySQL I've tried to make it work and I just don't think it's going to. Sadly, I would like to, but I just don't think it will.
Are there any plans for it though?
I don't know. It would require MySQL to change the way they handle triggers, and I don't know if they're going to. I wish they would, because I've seen other people complaining about it for unrelated reasons. So yeah.
Thank you.
Yeah, thank you. So, anybody else? Anybody else? Going one? Oh, somebody's standing up. More people are standing up. Are you asking questions or leaving? You can also leave. Okay. All right. Are we good? Okay. All right. Well, thank you very much.